Dear students, in this video, we are going to discuss very important antenna parameter, that is effective aperture area or antenna aperture area. And we'll bring a very most important relationship between directivity and effective aperture area. Effective aperture area.
Now, today we'll discuss another parameter and in the picture. It is also called as aperture, effective aperture, or it is also called as effective area. Also called as effective area. Effective aperture or effective area, it is represented A. Okay. For example, what is meant by this? Okay, for example, if this is the total antenna, if this is the total physical size, this is the physical size of an antenna. In this, for example, only this portion is receiving effectively the electromagnetic waves. Okay? This portion is receiving the electromagnetic waves effectively from this portion. And remaining, what about this portion? This portion is not receiving effective. Okay. So among the total portion, which is receiving effective, that is called as effective. Okay. Is called as effective area. Always the effective area is less when compared to the physical. Always the effective area is always less when compared to the physical area. The effective area is less when compared to the physical area. Compared to the physical area. Okay. So, what is the definition of an effective aperture? So, the definition of an effective aperture area is it is the ability of an antenna, the ability of an antenna to extract energy, from electromagnetic. Okay. So this is one definition of antenna aperture. So this is one definition of antenna aperture. Okay. Next, the other definition of antenna aperture is it is also defined as power received in the load, power received in the load to the average power density, at the point that effective area for aperture efficiency. A is also defined as power received in the load to average power density at that point. So therefore, A is equal to E received by E average. So by E average. Effective aperture area is equal to E is equal to E received by E average. Okay. So in other words, the effective aperture is an area which extracts energy from the electromagnetic waves out of the total area of an antenna. Okay, so let us bring an important derivation of the relationship between the directivity and effective aperture area. Very important derivation. Relation. Let us bring the relationship between the relationship between. So very, very useful and the most important derivation, relationship between directivity and effective aperture area A. Okay. So now let us consider an antenna. Okay. So let's consider, for example, this is my load. Okay. This is my antenna. Okay. So this is my antenna. This is my antenna. Let us consider the electromagnetic waves are coming in this direction. Electromagnetic waves, direction of electromagnetic waves are coming in this direction. So equivalent circuit is equivalent circuit is here. ZL is there. ZA is there. Okay, so this is the equivalent circuit. Okay, so let us assume a receiving antenna. So say this is, let us consider this is my receiving antenna is placed in the field of plane polarized wave as shown in the figure. Okay, having effective area A. Okay, and the receiving antenna is a Hertzian dipole terminated at considered the receiving antenna is a Hertzian dipole terminated at low impedance ZL. Okay, so ZL is equal to load impedance R plus J XL. Okay, so according to the maximum power transfer theorem, maximum power will be transferred from the antenna to the load if impedance is complex conjugate of the antenna impedance. Okay, so when will be the maximum power will be transferred from the antenna to the load? Okay, the maximum power is from the maximum power transfer theorem. You can say that this is nothing but ZL, the load impedance is equal to complex conjugate of antenna impedance. Okay, so in that case, whatever the maximum power that is received by the antenna, that will be equal to the load. Okay, so for example, ZL, the condition is to receive the maximum amount or maximum amount of radiation from an antenna to the load is the load impedance is equal to complex conjugate of antenna impedance. Okay, so what is the formula for the ZA? ZA impedance is equal to RA plus J X A complex conjugate. Okay. So that is nothing but RA plus J X. So RA means nothing but ZA means antenna impedance. This can be replaced with R rad as JX. Okay, so ZA conjugate is equal to RA minus JX. Okay, let us see here. We know that what is the condition for the maximum transfer? ZL is equal to ZA complex conjugate. Same place. With the value of ZL, the value of ZL is RL plus JXL. RL plus JXL. Okay, so it is plus JXL is equal to, what is the value of ZA? The value of ZA is, what is the value of ZA? R radius minus JXL. Yes, JX. Okay, so this one. Okay, so here if we compare the real terms and compare the imaginary terms, RL is equal to R rate. Okay, and imaginary terms XL is equal to minus X. XL is equal to minus XL, or XL plus XA is equal to G. XL plus XA is equal to G. Okay, so now here in this expression, this is my antenna. This is my receiving antenna. Okay, so in this, the total voltage, induced in the antenna, the voltage induced the antenna is given by. So you know that what is the relationship between the, what is the form of the electrical field? Electrical field is equal to the units of voltage per unit length. Okay, so unit per voltage per unit length. So the voltage induced in the antenna is given by the voltage is equal to E into dl. where DL is unit length and E is the electrical field. Okay, where is the electrical field at the point, and DL is the length of the Hertzian dipole. Okay, so length of the Hertzian dipole. Okay, so now the current traveling in the load is given as I is equal to, so I is equal to V by R. What are the two resistances we are having? ZA and ZL. Okay, so since okay, so it is equal to C by, what is the value of ZA? ZA already we know that R radiation minus JLCA plus RL plus JXL. Okay, so from this I is equal to OC by 2 R because RF is equal to and the value of XL plus XA is equal to G. XL plus XA is equal to 0. Okay, so therefore the value of current I, the value of current I is equal to VOC by 2 R. Next, power received by the load, received by the load is given as received is equal to I square R plus into R right. Square R plus into R right. That is IRMS means I can by root 2 F square into R right. Okay. So what is the formula for the IM? IM is equal to VOC by 2 rate. Okay. So therefore E received is equal to E received is equal to, in the place of IM I am replacing this one. Okay. So it is whole square is, that is nothing but VOC square by 8 R. Okay. So this is the formula for VOC because is equal to VOC by 2 R. Okay. So what is the formula for VOC? You know that the formula for VOC, the formula for VOC is E into DL. The formula for VOC is E into DL. Okay. Formula for VOC E into DL. Okay, simply substitute here. Therefore, power received is equal to E square into DL square. What is this DL? DL is the length of the Hertzian dipole. R. So this is power received by the load. Power received by the load. Okay, now the average power in Hertzian dipole. So this will be derived in the coming days. The average power of an Hertzian dipole is given as E average is equal to E square by 2 beta naught. Where eta naught is the intrinsic impedance. Eta is intrinsic impedance, that is equal to 120 pi. Okay. So therefore, what is the formula for the effective aperture or A is equal to PV received by E average. E received by E average. Okay. So this is the expression for E received. Let us consider this is K and this is P. Okay. So now substituting the values of A and B here. Okay, we'll get what is the value of P received. The value of P received is this one, that is E square into PL square by 8 R divided by E. What is the value of P average? P average value is E square by 2 eta. E square is going to get cancel ones to force. Therefore, the effective area A is equal to eta naught into DL square by 4 R. The effective area or aperture antenna aperture A is equal to eta naught is nothing but intrinsic impedance. So next the radiation resistance in this expression. So with the R rate it is radiation resistance. Okay, E is equal to that expression E is equal to eta naught into DL square by 4 R. Okay, so the radiation resistance of the radius, since we have constructed receiving antenna as H and dipole, the radiation resistance of H and dipole. This also will derive in the coming class. For time where it is given as 80 pi square into PL by lambda. It's very, very important. We should derive that. The radiation resistance of H and dipole is equal to 80 pi square into PL by lambda. In the place of R radiation, simply substitute that. E is equal to naught into DL square by 4 into 80 pi square into DL by lambda whole square. So lambda DL square okay, cancel, that is equal to eta naught into lambda square by 20 pi square. 20 pi square. Therefore, A is equal to eta naught into lambda square by 20 pi square. Okay. So what is the value of eta naught? Eta naught value is 120. So A is equal to 120 pi into lambda square by 20 pi square. Okay. So here pi will get cancelled. Zero will get cancelled. 4 3s 4 8s. Okay. So we get 3 by 8 square by 10 square by pi square. Square by pi. Okay. So we will just calculate it as 3 by 2 into lambda square by 4 pi square by 4 pi. Okay. So 3 by 2 means what is the value? 3 by 2 is 1.5 into lambda square by 4 pi. I can write this 8 as 2 into 4. Okay, so it is 1 pi. Okay, so very, very important thing we want to remember. Directivity of H and dipole is 1.5. Very, very important. The directivity of H and dipole is 1.5. This also will derive the next class. Therefore, what is the relation up to now? We have got A is equal to 1.5 into lambda square by 4 pi. Therefore, from this it is clear that A is equal to 1.5 by lambda square by 4 pi. But directivity of H and dipole is equal to 1.5. So in the place of 1.5, it should be replaced with the directivity. A is equal to D into lambda square by 4 pi. Therefore, directivity is equal to AD 4 pi by square. Okay, so directivity D is equal to 4 pi A by lambda. This is the most important derivation we will use in coming next semester, radars or all these expressions. So D is equal to 4 pi A by lambda square. D is equal to, this is the relationship between directivity D and effective aperture area A. This is the relationship between directivity and we will do so many problems in the next class. So this is in this, what are the things you want to remember? Here you want to remember that the directivity of Hn dipole is equal to 1.3 and the radiation of Hn dipole is equal to 8 pi square into dn by lambda. 8 pi square into dn by lambda. Okay, so this is the so we have started from here. Effective aperture area. So it is the ability of an antenna to extract energy from the electromagnetic waves. From the electromagnetic. It is also defined as the ratio of power received in the lead to average power density at that point. Okay, now we have already bring the relationship between directivity D and effective area AE. Okay, so I have considered an antenna. Let us assume the electromagnetic waves are receiving. This is my receiving antenna H1 dipole, and this is my load. So maximum power transfer theorem, the maximum of power that is received from the antenna will deliver to the load when T ZL is equal to complex conjugate of Z. Okay, so this is the equivalent circuit. Okay, so it's the things. So this is the final expression. This is the final expression which gives the relationship between directivity and effective aperture. It's the most important derivation in first unit.